Okay, so last Wednesday we moved on from talking about descriptive statistics, which we just use to describe our data that we get, say, from our scientific study. And we moved on to a discussion of inferential statistics. And those are the kinds of calculations we need if we want to try to generalize our data or findings to other groups or other situations, or make predictions about the probability, say, of something happening in the future. So once again, let's say we have taken a random sample of 100 data points of some kind, so a sample of 100. We know that's a pretty good size sample. And we have gone on from there to calculate our sample mean and the standard deviation of our sample. So that's a good start, right? But what we really want to do, of course, is say something about what we think the mean value would be for the whole population from which we took that random sample. And so, as you saw in Statistics Without Tears, we kind of do this by sort of pretending that we took an infinite number of samples from our population, even though we only take one sample, right? The equations sort of allow us to pretend that we took an infinite number of samples and then figured out the means of all of those samples and plotted them on a distribution, on their own distribution, and calculated the standard deviation of all of these hypothetical sample means. And you saw that what that really is that's how you come up with the standard error of the mean, okay? And once we have the standard error of the mean, we can then calculate a confidence interval, and that is just going to be a statement about the probability of the actual population mean falling within some range of values around our original sample mean, right? Because we're really only going to take one sample, and we want to know, how confident are we that the mean of the actual population that sample came from is sort of indicative of what the actual population mean is. All right, so once again, we have here a graph, and it shows a population on the graph here. The population is shown on the graph here by this black line. This is a nice population because it happens to fall into a normal shaped curve, okay? So once again, black line is our whole population, okay? And this red line curve, which is also a nice normal curve, that represents our distribution of sample means if we had, in fact, taken an imaginary infinite number of samples from that population and figured out the means of those infinite number of samples. Okay, so this graph, as we said on Wednesday, this answers the question about, well, if we figure out the distribution of sample means from our infinite number of imaginary samples, is that going to be more or less dispersed than the population? Will the standard error of the mean, standard error of this curve, be higher or lower, bigger or smaller than the standard deviation of our population line? Okay, and the answer to the question is that the standard error of the means is always going to be smaller than the standard deviation of the population itself. It's going to be less dispersed than the actual population because, in fact, when we set about to take samples of this population, right, the means of those samples are going to cluster pretty closely to the population mean itself. Okay, so one thing I want to talk about in this lecture is the really interesting thing that we need to understand is that no matter how skewed or wonky or weird our population data are, if in fact we take that imaginary infinite number of samples from that population, and if we graph the means of all those samples we took, we will always end up with a normal curve every time. So on the last slide, we had a population that happened to fall into a nice normal curve. But on this slide, I really want to illustrate this concept that if you take even an uneven distribution here of a population and you start taking samples of that and graphing the means of all those samples, you'll end up with a normal curve. Okay, so just to be clear, what do we have here? We have some data on, as you see down here on the bottom, body fat percentages of a population of women. Okay, so now a lot of times you don't even know how many entities your population contains, but for this example, we are assuming our entire population of women that we're worried about is 61. So our population itself is 61 women, okay? And in fact, we've sort of peeked behind the curtain here, and we know that our actual population mean is 28.7, okay? So that's unusual, right? That you would know your population mean, because usually you have a lot bigger population than 61, okay? But just for purposes of this example, I want you to sort of peek behind the curtain and be like, okay, our whole population is 61. We know the mean body fat percentage of our population is 28.7. Okay, so the next thing I want you to notice is that this is not a nice normal curve shape, right? It's skewed, right? It's skewed right because we're looking at which direction the tail is. So this is a right skewed curve of and the other thing I want you to notice is that the body fat percentages are put in here on a bar graph and they are binned. They are binned. Okay, so this and the numbers that are down below here are actually the center of each of these bins. Okay, and they're equal sized bins, and the center here is 19.9, 24.2, 28.5. So there are groups of women that would make up the parts of the population that are represented by these bars. Okay. Now, if we take from our whole population of 61 women, and let's say we take 10 samples, and each of our samples is going to have 10 women in it. So we're going to take 10 samples of 10 women each, okay? And with each of those 10 samples, we're going to calculate the sample mean, okay? And then we're going to graph that, which we've done here. And then we're going to figure out the mean of the sample means. The mean of our sample means of all 10 of those samples. And when this was actually done in this example, we find the mean of all of those samples of 10 was 29.4. 29.4, so something right about in here. So we actually got pretty close to the population mean by taking our 10 samples of 10. Okay, and the other thing we see illustrated here is the fact that the standard deviation of the sample mean curve, because look at, here's our sample mean curve, the standard deviation of this is much smaller than the standard deviation of the whole population that is shown in the pink bars. Okay, the other thing I want you to notice is look how the sample mean distribution is much more approaching the normal curve shape, right, than our original population was. Okay, the next sort of sample data I want to show you, the next way I want to illustrate this concept is with a population here. And what you'll notice is this is a bimodal distribution. So ignore right now the pink, okay? This very, very light blue and all of these bar graphs, this is our whole population. And you'll notice the curve goes up here, so we have sort of one mode, and then it goes down again, and then it goes back up again. It's called bimodal, even though these two values aren't the same, but it basically just shows that it's a kind of a double humpy set of data. So very weird data set with two peaks, okay? But so now, what have we done here? We've taken samples from this population, a whole bunch of samples, and each sample that we took a mean of that sample, okay, and we started graphing the means of the samples that we took from this population, okay? And once again, when we take samples and plot all the sample means that are shown in the pink outline, we end up with a normal shape distribution. Not only normal shape, but once again, less variance than this population itself, right? So the standard error of the mean here, once again, much smaller than the standard deviation of our main population. Okay, one more slide here just to make sure it's clear. So what do we have? 4 different possible population distributions. Okay, we have this nice, perfectly normal population. We have a right tail skewed population. We have another weird data set here of uniformity, right? And then this one is incredibly irregular, right? Up and down and kind of crazy. Okay, but what you see is that when we take samples and graph the sample means of all 4 of these very different shaped data set curves, okay, the curves down here, which are the graphs of the means of our samples, they more and more approach normal, okay? And the other thing I want you to notice, because this slide really well illustrates another point about the standard error of the mean that's in the book, and that has to do with sample size, okay? So you might remember from Statistics Without Tears that the larger the samples you take to do these imaginary infinite sample mean distributions, the smaller your standard error of the mean is going to be. Okay, and I'll send you back to page 92 and 93 of Statistics Without Tears if you somehow missed that. All right, but this should make intuitive sense to you because the larger the samples are, the less impact any outliers are going to have, right? And so the closer those sample means are going to be to the actual population mean, right? So you see, if we take our sort of samples of 3, okay, we do get a normal curve. We get something approaching a normal curve even with our weird distributions. Look at here, even over here with this irregular data set, we take samples of 3. But now on the next line down, we're taking a little bit bigger samples. We're taking samples of 5. So notice, number 1, how much faster it seems to approach normal. Okay, but also, look, the standard error of the mean is smaller each time. Each time the sample size goes up, we go from sample size of 3 to 5 to 10 to 20. Okay, and the same thing holds true with all of the different types of populations. So the larger your sample size, the lower your standard error of the mean is going to be. Okay, on this slide, I have a screenshot from one of the Khan Academy Statistics lectures that illustrates this same point. So for those of you who have never heard of Khan Academy, you'll see down on this slide, I have the website for Khan Academy, and I'm just telling you, this is, I forget what the gentleman's first name is, Mr. Khan, but he actually started doing YouTube videos for his nieces and nephews who were taking algebra or calculus, I forget. And these YouTube lectures were so popular among people all over the world that he started doing lectures on any number of topics. And he has incredibly good lectures on statistics. So I would highly recommend, if you're having any difficulty with this, go ahead and Google Google Khan Academy Inferential Statistics, and on that main page, you're going to see a set of lectures, if you scroll down, on sampling distribution, which is just what this is about. And I think he has a great lecture style, and it's really easy to understand. Okay, so just as an adjunct to this and to class, or also for your future legal work, if you want help understanding some statistical or scientific concept, I highly recommend the Khan Academy lectures. Okay, so this is a screenshot from one of those lectures illustrating this same point that I've just been making in the rest of this video. So, and that point is, the larger the samples that get plotted for our, to determine our standard error of the mean, the tighter the normal curve of those sample means are going to cluster around the actual population mean. So here in the upper left, you see, here's a little drawing that Mr. Khan has made of his weird population distribution, very irregular. Now what he does is he imagines taking an infinite number of samples from this population and graphing the sample means. That's what we've just been doing the last few slides. Okay, and so what he has on this slide is what the sample mean distributions might look like if you took an infinite number of samples of 10, an infinite number of samples of 20, and an infinite number of samples of 100, okay? So you can see he says, okay, if I took samples of 10, my sample mean distribution might look something like this, okay? With, standard error of the mean, right in this area, right? And if we move it up and double that sample size, look what happens. The normal curve gets higher, because it's bunched more closely around that center point, okay? And our standard error is going to go down. And then down here in the left lower corner, we actually take the original sample times 10, and we have these very large samples of 100, and look how much lower our standard error then becomes with those larger samples. So the larger the samples, the smaller the standard error of the mean, the tighter those curves are to the mean. All right, and in class on Monday, I'm going to also show you another website that has a really great simulator that is sort of fun to illustrate this concept as well. And that's the end of lecture 4.